Okay, so let's get started. I was not able to upload the lecture. I had gotten it done from yesterday, but I'm sure the snags would be taken care as we go forward this week. Partly the reason why we had the class today and probably we'll have tomorrow also is to make sure that the first week classes are done and at least you guys have enough lectures to decide about the course and its content and the way it is delivered. Okay. So now let's start today's lecture. Any specific questions from anyone? People who are online, please feel free to unmute and speak up. Any questions? No? Okay. There is one
No
more thing
questions.
that no questions. Thank you, Priyadarshini. There are a couple more things that I have to clarify. Quizzes plus assignment for Bhopal would be somewhere around 30% weightage. Okay, 20% for the quizzes and 10 for the assignment. I'm still working out how the assignment would be. Mid-semester would be say 30% overall and end semester would be 40%. This is for Bhopal. And for Thiruvananthapuram and Pune, each of the respective advisors will share. We'll mostly post it on the classroom specifically for you guys so that that's also clear as we go forward. I hope people remember that the quiz dates or the weeks have at least been already informed. So 31st, the week of 31st August will be your first quiz. The week of 2nd August would be the second quiz. Midsem will be already decided. That's been already decided by academic office. So is Ensign. Okay. I hope assessment related stuff has been clearly told to you guys now. Okay. So now, what do we hope to learn today is to further our basics in the field of NMR. So let me take one step at a time. This will be a semi-classical way of understanding how NMR spectroscopy works. I'll try to justify what's semi-classical. So let's divide the word nuclear magnetic resonance into three parts. We'll be trying to understand what's nuclear about it, what's magnetic about it, and why is it a resonance-based spectroscopy. Okay, in last week class, I was trying to hint that whenever there are enough energy levels, I mean, at least energy levels that are separated by a certain energy difference, one could end up shining light at it, taking the response out of it to do spectroscopy, right? And we were trying to highlight the fact that as you keep changing the source and the energy levels that you're perturbing, you would be able to learn different aspects of the same molecule. For instance, you can always subject the same molecule to any different type of spectroscopy to get a specific spectrum. Can one of you guys tell me why would we want to have so many different spectroscopic techniques to characterize the same molecule?
For authenticity of the item.
Yeah, but how? But why so many? Just choose two and get it done.
Technique have some limitation.
Okay, so each spectroscopic technique has a limitation. Fine. So what? Why cannot one technique be enough? Correct? Give me an example. What do you miss out? Take an example and try to highlight to me what if when you take, you might not be able to distinguish. Take simple examples. It need not be, real experimental data, but
Suppose to example like UV. UV we can get like the absorbance, right? There we cannot get higher resolution like atomic information. Instead, like NMR, we can get every atomic details of the molecule.
But are you trying to say NMR spectroscopy can distinguish any two different types of molecule in every possible scenario?
No, not every possible.
Give me an example where that fits.
Okay, like if the concentration of the molecule is so less, if the molecule is so large, like in terms of like bigger protein and this thing.
I see.
NMR still.
Right. So, okay, basically the need for multiple different techniques comes from the fact that, let's say we take the entire population of this class or any other class, and we want to classify them based on who are all there. There are some specific features that we would end up taking. Okay, let's check gender, male, female, let's check height, let's check weight, let's check eye color, hair color, wearing spectacles or not, and so on and so forth, right? So now the thing is that I'm sure if from an entire class there'll be multiple people who would be binned at the same weight or height or male, female and whatnot. So the more and more techniques we end up employing, each one of the technique gives a specific feature as we end up perturbing different energy levels. Meaning that for some systems that have similar nuclear spin energy level distribution need not have the same mass and vice versa. Okay, so when you're taking something like butane versus isobutane, mass spectroscopy is not going to be useful. I mean, some type of mass spectroscopy is not going to be useful because you're going to get the same mass, right? So therefore, each technique has its own advantages, and NMR is one such technique which has its own advantage and disadvantages. So many advantages and few disadvantages. So therefore, we want to end up ensuring that we highlight each one of them to understand which technique to be taken at what point of time. Since we are trying to only learn about NMR spectroscopy, let's talk about what energy levels come up and what do we learn from them, and are there any disadvantages that these end up causing. So first of all, the question arises for NMR spectroscopy, which energy levels are we perturbing? So here is where I have to invoke a bit of quantum mechanics, and people who do not know, do not worry about it. What I'm trying to make you understand is that I'm sure you would have learned something about a wave function, where we tend to attribute the aspect that the wave function has all necessary information that you want to extract from the system, right? And I'm sure in your basic quantum mechanics course, you would have seen that the wave function for a certain system is dependent on the spatial coordinates and time coordinates, right? R and T, where R could be XYZ in three-dimensional Cartesian coordinates, where T is time, right? And we learned many features of this, and once we learned all features of the wave function, we were able to extract specific information that you needed, right? And therefore, what I'm trying to highlight here is that if you have the information of the wave function, you could extract out a lot of information that is of interest to you, right? So similar is the fact, of course, here we are talking about chemical entities, right? A molecule's wave function, and that's going to be quite complex, meaning that you have so many atoms that are being present, right? And each of the atom has its own XYZ coordinates based on where the atom is positioned in the molecule. And each of the atom itself has its own electronic properties, which has its own N, L, M, and MS, ML quantum numbers, and MS, which is the spin quantum number for the electrons. So you realize that this has way too much information. And how are we going to extract, and what all parameters are important? This is where life makes it very easy for us, where you can divide it into, let's say, two different parts of wave function. Just for the sake of it, I'm writing some symbols here. Don't take them too much to heart. Where all parameters except for one parameter goes into one part of the wave function. What do we mean by it? The position, the in translational degrees of freedom, vibrational degrees of freedom, rotational degrees of freedom, everything that you can imagine, even the electron, the diamagnetic cloud. Generally, we are talking about chemical entities which are diamagnetic in nature. So all such information gets bundled up into theta. And you can imagine the psi that you're trying to look at here is containing the one important parameter that you want, which is what distinguishes the energy levels. So the wave function, this part of the wave function is more than enough. And as we go forward, we'll realize we don't need the absolute form of the wave function. We'll be able to attribute it for some of the spin systems that we are working, and in a very simple basis set, which is not infinite. Okay? What do I mean by that? It's a finite basis set that you're trying to use. Why am I emphasizing on the basis set? I'm sure you guys would remember from your quantum mechanics is that, so therefore, if you know the basis set that is involved, the wave function can always be written as sum of, can be written as a superposition of wave functions, correct? And therefore, unlike the quantum systems that you're comfortable with in terms of particle and a 1D box, particle in 2D, 3D boxes, particle in a ring, rigid rotor, vibrational, the harmonic oscillator, or the hydrogen atom. There, if you realize, there was no bound for the quantum numbers, right? It could take literally almost infinite values. And for every value, there will be certain level of degeneracy associated with the model and whatnot, right? On the other hand, here, our life is pretty simple. Now I have to introduce what part of that wave function that we are trying to use. We are actually going to be using only the nuclear spin component of the entire set of information that is being present. So what do I mean by it? Don't worry if you don't understand what this means. There are so many parameters that are within the major wave function. Let's say there are n parameters involved. I'm saying put n minus 1 in this part of the wave function, have only the nuclear spin component in this part of wave function. And I'm sure this is quite comfortable for you guys because we have done the same approach for even the hydrogen atom when we learned the quantum mechanics, right? Where you would have psi n l m, which would be written as r of r times something like theta of theta comma phi, right? Even that could be broken down, where you would have a theta of theta component and a phi of phi component associated, where this will be related to quantum numbers that are defined by the theta part. I'm sure you guys remember. If somebody does not remember, please let me know. I'll try to add a little more details to it. Makes sense? So therefore, you can divide things across into smaller components, and we will only query based on the component that's going to be disturbed by whatever we are trying to do, right? In the phi part of the hydrogen atom, you realize that it's an e power plus im phi, where m is one of the quantum numbers. So if you are trying to talk about the Lz, which is the z component of the angular momentum, you only worry about the phi part, because Lz operator is, if I remember right, is minus IH cross dou by dou phi. So basically, it's only going to be perturbed or be queried by the phi component. So you don't have to worry about the rest, right? So similar is the aspect where you can separate the component that matters the most for NMR spectroscopy, which is the nuclear spin quantum number. Okay. Now coming to what's the nuclear spin quantum number, for all practical reasons for this course, you can take this as an intrinsic parameter of an element. What do I mean by this? For a given element, its nuclear spin quantum number is fixed. That cannot be changed. And if you're really inquisitive to understand what drives the nuclear spin quantum number, it is decided by the components of the nucleus. What are the components of the nucleus? Proton and neutron, right? Can you go further? Can they be divided further than this? Yeah, what are they called? They are called quarks, right? Subnuclear particles. And each of them have their own, say, mass, spin, and properties, right? So yeah, broadly speaking, the nuclear properties determine the nuclear spin. But given that for every element in this earth within ambient conditions, the nuclear properties do not change, is that right? Except for anything like a nuclear fission or a fusion that happens, the nucleus remains intact. As chemists, we are more concerned about the changes that happen to the electronic environment or the number of electrons that are being present, but not of the nucleus, right? Except for nuclear chemistry. We'll keep that aside for the discussion on this entire course. So what I'm trying to say is that the components of the nucleus decides this intrinsic parameter called the nuclear spin. Okay? So therefore, for every given element, the nuclear spin is already decided, and it will not change. The best part about NMR spectroscopy is that you're using radio frequency waves, which even does not perturb the electronic energy levels. You can't disturb the electronic energy levels. Nuclear energy levels are far much more separated that they will never be disturbed at all. Make sense? Yes? It's something like when you're making a measurement of your body weight, your body temperature does not change. These two are not same parameters. So if you're trying to perturb one, the other one will never even feel it, right? And especially if you're imagining nuclear spin energy levels are really close to each other, electronic energy levels will be far away, and I can't even draw where the nuclear energy low is. They're so much far away that they will never be disturbed by the very weak perturbation that we are performing. Make sense? So let's further dive into detail on how each element's nuclear spin quantum number comes up. Why are you spending this much time? Because you will soon realize we are going to attribute it with a quantum number I. If the I quantum number is 0, you cannot perform nuclear magnetic resonance spectroscopy with it. Okay? If I is 0, no NMR. This is important for us to recognize and understand. Okay? So for instance, let's take any element which has an even, meaning even mass number, even atomic number. For all these kind of systems, the nuclear spin quantum number is 0. There are umpteen examples of this. One of the most common ones is C12, right? O16, right? Sorry? Wrong. So these are the ones which have an even nucleus that makes the spin quantum number, nuclear spin quantum number is 0. Okay, makes sense? Then you have other examples where you have something like which has an odd. What number is that? Mass or atomic? Mass number. Okay. So that determines the overall qualities of the nucleus. Yes, no? Which one is it? Is it this one or this one that determines the nucleus part? The any part or the odd part? Odd part, I see. Okay. So let's take some examples here. We'll come to it. 1H1. So these are kind of nucleus which have n by 2 spin quantum number, half integer spin quantum number. For instance, 15n, 14n. No, this is right, 15n. 15n, 7. Let me think of 17O8, then 13C6. All these have n by 2 spin quantum number. Okay, and in particular, some of the elements that are of interest to us, I think even 31P, 19F. So many of these have spin quantum number n by 2. In particular, we will be focusing on systems that have a spin quantum number of half. I'll come to that in a moment and why that is the case. I think this is 3 by 2, I forget. It's one of the quadrupolar nuclei. I'll define quadrupolar nuclei after the next one. So the next one that you have here is something that is even and it is odd. We just took an example of even. Okay, the only other combination that's left out is even odd. So when you have something like even odd, these will have spin quantum number that are integer in nature. For instance, this is where 14n7 would come up, 2h1 would come up, okay? And there are many such more examples, okay? And for instance, N14 is spin 1, so is deuterium. Deuterium has a special place in nuclear magnetic resonance, which we will see a little later as we go in the course. Makes sense? So what did we start off with? We said if we have energy level separation, then we can do spectroscopy with it. Therefore, if we have the complete information of the wave function, we can exploit it. Okay, do we need the entire wave function? No, not really. If you have the nuclear spin part of it, that is enough. Then the immediate next question comes up is that which ones have a nuclear spin component that is important for us to consider. And therefore, we are defining some very basic, let's say, features that we can immediately figure out whether a certain element from the periodic table has a nuclear spin quantum number or not. Make sense? And especially if you have a nuclear spin quantum number of 1, then NMR spectroscopy is not very useful there. Just to emphasize the importance and the reason why NMR spectroscopy is so predominantly featuring in a chemistry department and also quite a bit in physics and biology department is because except for two elements in the periodic table, if I'm not wrong, argon and cerium, all the other elements at least have one element that has a non-zero nuclear spin. Let me repeat that again. In the entire periodic table, the mere fact that only two elements have nuclear spin quantum number is 0 makes NMR a super powerful technique. That means that literally almost every element in the periodic table could be potentially studied with this phenomenon. Does that make sense? Yeah. So that makes it an extremely powerful tool. And of course, there are some features that makes us like the spin half system. So anything which has spin quantum number greater than half are called quadrupolar nuclei. What do we mean by this? For almost all spin half systems, it has only the nuclear magnetic component associated with it, no electronic components that are being present. As a quantum number goes more than half, literally even for something like 1, 3 by 2 and so on and so forth, there are additional features that get added on top of it, meaning more energy levels and separations start to come. And therefore, there are other attributes that go with it. So generally, they are referred to as wherever you end up exploiting quadrupolar nuclei for your spectroscopic techniques, it's often also referred to as NQR, nuclear quadrupolar resonance. Okay. So for the predominant duration of this course, we would pertain ourselves with spin quantum number of half. I'll try to justify by today why that is the case. Any questions? People who are online, please feel free to unmute and ask if you have any questions. So I'm going to go ahead. So we have now defined if there's a non-zero nuclear spin quantum number, we can do NMR. Especially if it's spin half, we like it. We'll try to define why we like it as we go forward. The moment you have I as half, the allowed values of Mi are going to be given by the I quantum number. It's very similar. Let me write it on the side. Similar to L and ML. You guys remember L and ML quantum numbers? Where the L quantum number decides the range where ML can go. And literally it is the same, even whatever we are exploiting here is literally the same, meaning that if you have spin quantum number I, the Mi also goes the exact same way. Meaning that the Mi can go between minus I plus 1, minus I plus 2, so on until I minus 1 to I, all in integer steps. And therefore, if you are able to realize for I as half, 2I plus 1 states are available, right? 2L plus 1, no, it's 2I plus 1, that's it, right? So how many states are allowed for a spin quantum number of half? You're going to have two states that are going to be present. 2 times half plus 1, which is 1 plus 1, which is 2. Okay, this is once again what makes the study of nuclear spin half systems more common than any of the other ones, meaning that the number of states that are being present are just 2. Isn't that wonderful? They're not infinite states. Now realize, what do I mean by this? Let's attribute it to a few aspects. Let's say quite commonly the Mi of plus half is represented as the alpha state, and the Mi of minus half is represented as the beta state. If you once again observe, I'm quickly jumping onto the Dirac bracket notation, right? This is the Ket notation, which indicates a given state, right? And remember, once again, when we learned in a quantum mechanics course, these form a complete orthonormal basis, which means that if these are eigenfunctions of the nuclear spin operator, then they are orthogonal to one another. What do I mean by this? Alpha beta and beta alpha are orthogonal to one another. If you integrate over all space for the nuclear spin part, alpha and beta have no overlap on each other. Of course, this also implies these are normal basis sets Okay. So therefore, what this gives us an idea is that two energy levels are being present for spin half systems. Okay. Let me ask a quick question here. People who know the answer, especially people who are registering and people who are online, please raise your hand. I think I should be able to see it. Now, are these energy levels sufficient for us to do spectroscopy? People who want to say yes, raise your hand. May I ask you repeat the question again? Let's say you have two energy levels. Okay, great. Let's start doing spectroscopy. Is that a sufficient condition for us to now have two different energy levels for these two states and start doing spectroscopy? Nobody? Anybody? Please raise your hand online or speak up here, please. Okay, since everybody is silent, let me go ahead. Okay, there's one hand. Deeptanu, please go ahead and
Yes,
speak
so
up.
the energy levels should not be degenerate. We need to split the degeneracy to get
Okay,
any.
excellent. That is the point. So when you start off with this, okay, Deepanta, don't mute yourself. Sorry, Deeptana, don't mute yourself.
Yes,
You see the two energy levels, and yeah, you're totally correct. So they are degenerate in nature. So if you are degenerate in, if the energy states are degenerate in nature, the populations on both the states are equal. Correct?
yes,
Yeah. Now tell me, how would you break this degeneracy?
yeah. So
So no spectroscopy. Sorry,
applying magnetic field probably.
why not an electric field?
Yeah, yes.
Okay, what is that effect called if you apply a magnetic field?
Uh,
Do you know a
Zeeman
name for it?
effect.
Yes, that's right. It's called the Zeeman effect. I'm sure you guys would have learned this in your chemistry course as well, where when you have, you may mute yourself, Deeptanu.
Yes,
So when you put these two in an energy level B naught, they are going to get separated. We will see in a moment how this separation starts to come, and we will also attribute it to which energy levels go where in one moment. Let me repeat again. These end up behaving very similar to the LML, and if you are not able to relate to it, let's relate to this concept by recollecting how the degenerate p orbitals behave. If you are having a p orbital in the absence of a magnetic field, they are all degenerate in nature for the hydrogen atom, of course, right? And then the moment you start to introduce a magnetic field or an electric field in that example, then you start breaking the degeneracy. On the other hand, in this case, applying an electric field will not have an effect, which is exactly why I spent a little bit of time explaining the nuclear quadrupole spins. For spin-half systems, there is no electric component associated with it. So if you end up applying an electric field, the energy levels will still be degenerate. Okay, so you must apply a magnetic field in order to make sure that you are able to split the degenerate nuclear spin energy levels. Yes, Deeptanu, you seem to have raised your hand.
so it was
Oh,
just
okay.
previous.
Previous one. Okay, okay. Hey, good. Actually, it starts to pop up here. So students, please raise your hand. Or yeah, if you raise your hand, you'll be able to see, and I can pause so that you can unmute and ask your questions. Okay, good. So far, good progress have been made. We are trying to say nuclear magnetic resonance spectroscopy is related to the nuclear spin quantum number, and that's attributed to the mass number and atomic number of a given element. Since most of these are accessible, NMR is a super powerful technique, and predominantly we'll be focusing on spin half systems in this course, and spin half systems have two energy state, the two eigenstates which are denoted as alpha and beta, right? And these energy states are degenerate in the absence of the magnetic field. The moment you put them in a magnetic field, which we are going to call as B naught. So from now on, B naught will be referred to as the static field, the static external magnetic field. and so on. Okay, there are different names that you'll give. But whenever I say B naught, remember the B naught has to always exist for you to do the spectroscopy, right? And this is also what makes NMR a super expensive technique, because the B naughts that we are talking about are in the range of Tesla. Okay, magnetic field is generally given the unit Tesla, and the magnets that we are talking about are in the range of 10 to 20 Tesla quite commonly. Can somebody tell me what is the Earth's magnetic field approximately? 14 Tesla. Earth's magnetic field. Can't be 14 Tesla. We won't be alive. Or at least we would be more magnetic than what we are right now. Can anybody answer what do you think is the Earth's magnetic field? So it's about 10 micro Tesla, approximately. Okay. So what we are talking about here is about 6 orders of magnitude higher magnetic field. It is an extremely powerful magnet. And to achieve this, one has to end up having superconducting coils. And the superconducting coils by themselves are expensive, and they have to be kind of immersed in a bath of liquid helium, which is once again more expensive, making NMR quite an expensive technique. As I said, we'll highlight the positives and negatives of NMR. So far, this is one of the small limitations that comes up. Of course, money in science is important, but not any more important than the information that you want to extract. Therefore, this is able to give some specific information. Therefore, this technique also finds its place in extremely critical labs and research questions that we try to answer. Okay. So I would like to highlight that the magnetic field that we are putting our spins through is extremely high magnetic fields. And if any of you have experienced MRI for yourself or your family or friends, you realize that you would have gone into a magnet. So basically, that's where you're actually doing NMR of yourself. Okay, and those magnets are a little more weaker than this. I want to say something in the order of say 5 Tesla, 5 to 6 Tesla. They are weaker in magnetic field because you cannot make such big magnets at high fields. Okay, so now coming back, you have degenerate nuclear spin energy levels. You suspend them in an external static magnetic field B naught. I'm repeating the word static because the magnitude of B naught will never change the moment you put the sample in the magnet. The B naught will always remain, and therefore the nuclear energy levels will be split. How much do they get split? We will see in one moment. Okay? Okay. So now what we have here is that immediate question that comes up, what is the energy for each of the state? If you guys remember from the classical component, it would be given as minus mu dot B, right? Of course, when you go to quantum mechanics, you're going to write the same thing, but in terms of operator, right? Generally, we will attribute the B naught, or rather reference the B naught to the Z axis. What do I mean by this? Whichever axis the B naught field is aligned will be referenced towards the Z axis. This yet again is very similar to the argument which you would have learned in your quantum mechanics on why whenever you do something, the LZ and L square operator are invoked, because you realize that L square, the total angular momentum operator, the square of it, and the Z projection of the angular momentum operator, they commute with each other. And in quantum mechanics, we used to love operators that commute with each other, largely because if you find a basis set with one, you can use the same basis set for the other. Yet again, it goes back to the Heisenberg's uncertainty principle that if you have two operators that commute with each other, the uncertainty, both can be measured simultaneously precisely, right? So there we ended up choosing the Z component significantly because the representation of the Z operator in spherical polar coordinates was the simplest. Okay. So similarly, we will end up, since all the operators we are borrowing from the angular momentum part, we can happily say the B naught is aligned along the Z axis. Make sense? Yeah. Okay. With that being the case, so what does B naught reduce itself to? B naught reduces itself to B naught times K, where K cap is the unit vector along the Z axis in the Cartesian space. Make sense? Everybody comfortable so far? What is mu? It's very interesting. What is mu? Mu is directly proportional to the spin quantum number. Not quantum number, the nuclear spin vector, right? This is the magnetic moment. This is the magnetic field. This is one of the main reasons why I started writing things out. B is referred to as field, while mu is referred to as moment. Moment is an intrinsic property of the magnet, while B is the field that you suspend the magnet in. I'm sure all of you have played with bar magnets. When you suspend a bar magnet in an Earth's magnetic field, the bar magnet has its own magnetic moment and it interacts with the Earth's magnetic field. How would the bar magnet align itself over a period of time if you suspend it? Parallel or anti-parallel? The Earth's magnetic field. Parallel. More louder and clearer and more confident, please. So it will align itself parallel because you see there is a minus sign here. I'm missing the dot. Please make the dot prominent. This is a dot product, which is a scalar product, which means that this is going to go minus mod mu mod B cos theta. Right? Yeah? When is cos theta highest? When theta is 0, right? When theta, therefore, the bar magnet aligns itself parallel to the Earth's magnetic field, correct? We'll come to quantum magnets in a moment, which have their own differences. So therefore, what you're able to see here is that the magnetic moment is directly proportional to the nuclear spin vector, right? And the proportionality constant is going to be referred to as the gyromagnetic ratio. It is also referred to as the magnetogyric ratio. It's, if I'm not wrong, it is the ratio of the magnetic field to its radius of gyration. So which is why the word magnetogyric makes more sense than the gyromagnetic, but the field ends up using the term gyromagnetic ratio. And yet again, this is a intrinsic parameter. Yes? We will come to it in a moment. It's a vector, but then now I went to the quantum mechanical this thing. So I'm trying to write it as operators in operator space, right? This is something that we do commonly in quantum mechanics. You take the classical expression and convert it. Second postulate of quantum mechanics says for every physical observable, there's an equivalent quantum mechanical operator. So I'm just doing that. Okay. If I'm doing some mistake, please highlight. Okay. So similar to the fact that I said, each element has a nuclear spin and it's a constant. For all practical purposes of this course, we can assume the gyromagnetic ratio is a constant for every element that you're working with. And it is different for each element. Okay. Now I'm going to further divide the nuclear spin vector or the operator, nuclear spin operator. In three-dimensional space, how are you going to represent it? It's going to go as further division based on, okay, I'm going to drop the cap for the unit vectors. Okay. So basically, this is representation of the nuclear spin vector in Cartesian space, where Ix, Iy, and Iz are the projections of the nuclear spin on each of the axes x, y, and z in the Cartesian frame. Yet again, if you're getting confused and if you're worrying what is this, you can have the direct correspondence to each one of them, as the L vector is Lx I plus Ly j plus Lz k. Literally whatever you learnt in quantum mechanics for the hydrogen atom, for the angular momentum component can be borrowed here directly. Okay. Now, therefore, let's try to ask what will be the overall Hamiltonian. Hamiltonian is minus mu dot B, which is going to be minus, I'm going to take the gamma out, and you're going to have Ix I plus Iy j plus Izk times B naught times k. Remember, there is a dot product there, right? So what does this reduce itself to? Minus gamma B naught Iz, because you have only k cap when with respect to the field, and therefore these two components do not end up coming up. So far so good. Okay. Now what we have is an expression for total energy based on the z projection of the operator. Okay. Now let's ask a question. What is the next thing that we do? We said that for I equal to half, the allowed values of mi are plus and minus half. We said mi of plus half, we will call it the alpha state. Mi of minus half, we'll call it the beta state. So the first question that comes to your mind is that let's apply the Hamiltonian on the alpha state. Okay. So what is that going to become? Minus gamma B naught Iz on alpha. Right? And what do you think will be the outcome of this? You're trying to take the z projection, and you already know the z projection for this is half. So this is going to be minus gamma h cross B naught by 2. Whenever you're making a measurement, the h cross times this thing would come up. Okay? Right? And therefore, this is what is the energy level for alpha. Many times in some textbooks, they would set h bar as the unit of measurement in the quantum space and may not write the h bar. It's implicitly assumed that it exists, and they'll kind of write only gamma B naught by 2, minus gamma B naught by 2. Okay? And then you have Hamiltonian on beta. That's going to be minus gamma B naught Iz on beta. What are you going to get out there? You're going to get a minus half h cross out. So minus of a minus becomes plus. So that becomes gamma h cross B naught by 2. So now, given these two cases, which one do you think would be the ground state? Would it be the alpha or the beta spin? Louder? Alpha. So the answer that I get is that alpha will be the ground state. Yes, you are correct, provided you assume gamma is greater than 0. So this is why I told it's an intrinsic parameter and did not explain much beyond that, is because gamma at times can also be negative. Less commonly, but that is possible. Okay, for instance, 15N, the spin that we were talking about a moment earlier, 15N has a negative gyromagnetic ratio. At that point, the beta becomes the lower energy, alpha becomes the higher energy. Okay, so please be aware. But since most of the spins have gamma greater than 0, alpha will be the ground state, beta will be the excited state. And most importantly, the delta E that you want to determine between these two is going to be excited state minus ground state. The ground state has a minus inside itself. So that makes it Sometimes when I write fast, I make such mistakes. Please feel free to point it out to me. Okay. So now what you're able to see here is that the delta E between them is driven by B naught. What does this signify? Remember, gamma is a constant. I'll come to it in a moment. H cross is a universal constant. the measure of the quantum space, and B naught is the external static magnetic field that you are applying. So major take home message that you get here is that as you increase B naught, delta E increases, right? And if delta E increases, I pointed it out in the last class, we'll see more detail in the next class. The population difference would also increase. The energy difference between the states increases. The ground state will be more and more populated than the excited state. So this is one of the main reasons why NMR spectroscopy becomes even more expensive, because people keep chasing higher and higher magnetic field strengths. Yes. That's because if you may recollect one of the expressions that I pointed out to, not sure where it is. Here you have two energy states. By Boltzmann's distribution, if you have the excited state, the ratio of the populations in the excited state to the ground state, it goes as e power minus delta E by kBt. As delta E increases, you would realize that this will keep reducing. The ratio will keep reducing, meaning that the ground state is more and more populated with respect to the excited state. We will actually see the exact expression for it for some systems tomorrow in tomorrow's class. At that point, it will be more evident to you. Okay? Okay, so now let's take some example of gamma. Gamma H, I think, is 2.7652, 10 power, I think 8 or 7, 10 power 8, I think. Radian per Tesla per second. Okay, and why am I trying to put it out here is that if you end up trying to check the gamma of carbon, it is about 1/4 of gamma of hydrogen. So let's try to highlight the energy difference. People who are working very hard to write the notes, I'll share the notes. Please focus and understand. So in addition to having B naught that drives the energy difference, I'd like to highlight the fact that the gyromagnetic ratio also ends up driving the energy difference. One of the elements that has the highest gyromagnetic ratio is actually the proton nucleus. There's only one other nucleus in the periodic table which has a higher gamma than proton, which is tritium, which is an isotope of proton, 3H, but we don't end up using it because it's radioactive. And it's also the abundance is so low that we can't use it. And the increase in gamma is about 5% more than that of proton, so it's not much of a difference. Okay, so when I say next time gamma is the highest gyromagnetic ratio spin, we'll take it for granted, although trivia-wise that's not true. But the one that's accessible is proton. And the next most important element that we would like to see as chemists is carbon. And you see that the carbon's gyromagnetic ratio is 1/4. What I would like to highlight here, for the same static magnetic field, you suspend your nuclear spins. For the same molecules, same bonds that you're trying to see between C and H, the C has a C13 and H has 1H. The 1H energy level differences are 4 times higher than the carbon energy differences. And this yet again highlights to you, therefore, a proton NMR spectroscopy experiment would have higher population difference and therefore more sensitivity than a carbon. So I told you guys that when we started off saying that spin half systems are most accessed because there are only 2 energy levels. Now go to the spin 1 system, there are going to be 3 energy levels. So as one of the homework that I would like to give today, so repeat whatever discussion we did for spin 1. Draw the energy levels, find the energy gaps between the energy levels that will be present with respect to the magnetic field and a certain gamma. Assume gamma is a constant. Very simple, same extension of spin half systems. Okay? And then what I would request you guys to do is to get familiar with gamma of few spins. Which spins are these? List. When I say homework, I expect this to be done before the next class because I'll be using it. I'm not going to be testing whether you want to submit. We figure out a mechanism for it as we go forward. Gamma for 1H, 13C, 15N, 19F, 31P. Should be, most importantly, I forgot deuterium. Should be kind of in your head. Okay, you don't need to know the exact values for these. The moment you know proton, and all you need to know the ratio with respect to proton. For instance, nitrogen is about 1/10 of proton. Okay, fluorine is about 475 megahertz on a 500. Probably 5% difference. Maybe Jeet can tell a better number. Phosphorus is about 60% of proton. Or is it 40% of proton? No, it's 40% of proton, not say. So basically, carbon is 25% of proton, nitrogen is 10% of proton, and phosphorus is about 40% of proton, and most importantly, deuterium. Deuterium is about 1/7 of proton, 1 by 1.67. Okay, so these relative numbers would be helpful to have. And homework number 3, calculate delta E in terms of hertz. Okay. So with that, I think we have to stop the class given that it's 9:55. Any quick questions from the Pune or Thiruvananthapuram? Please raise your hand on the Zoom platform. Okay, if there are no further questions, I'll try to upload both the lectures from first class and today by today evening. Tomorrow we will meet again by 11 a.m. Sorry that we are having back-to-back classes, which we will avoid as we go forward so that we can keep up with the lectures for a given week. Thank you so much. Have a nice day.